If you had the chance to travel back in time, say to the age of the dinosaurs, what tool would you take with you on the journey? Ask an astronomer, and chances are they'd name a telescope. It's incredibly fascinating to look at the night sky, and even more so to aim at Saturn. But would they actually see the famous rings? Well, that's a matter of debate, because the age of one of our solar system's most iconic features is still not fully understood. There's a strong possibility that we're witnessing only a brief phase in Saturn's life, when it happens to have this majestic ring system. Regardless, right now the ringed planet is breathtaking. Its grandeur has inspired generations of astronomers to gaze through telescopes and explore the universe. So now it's our turn to talk about it, to understand the nature of its rings and many other unique features. Of course, 30 minutes won't be enough to cover everything comfortably, so expect at least a second part, which we'll dedicate to Saturn's moons. For now, sit back and enjoy. The 1970s were a remarkable era for space exploration. Scientists had a thrilling opportunity, a rare planetary alignment that occurs only once every 175 years. This configuration allowed spacecraft to travel from one planet to another using their gravity to gain speed. We all know about the Voyagers, the missions that revealed the outermost corners of our solar system in stunning detail. But before launching them into the unknown, NASA needed to answer a big question. Could spacecraft even survive a journey through the asteroid belt and endure the intense radiation around Jupiter? So, before the legendary Voyager missions, NASA decided to send out 2 other spacecraft to blaze the trail. These pioneers, literally, were called Pioneer 10 and Pioneer 11. Pioneer 10 launched on March 2, 1972, heading toward Jupiter. Pioneer 11, launched a year later as a backup, followed the same path. But once Pioneer 10 successfully reached Jupiter and completed its mission, operators decided to give Pioneer 11 a new destination, one just as fascinating. Before reaching Jupiter, Pioneer 11 performed a trajectory change maneuver and, using Jupiter's gravity, swung across the solar system toward a new target, Saturn. On September 1, 1979, Pioneer 11 flew just 20,900 kilometers above Saturn's cloud tops and took a total of 440 images. This first close encounter of a human-made probe with Saturn gave scientists valuable data about the planet's magnetic field and atmospheric composition. Pioneer captured images of Titan, appearing as a blurry orange-hazed sphere. Astronomers also identified a new ring, now known as the F ring, and discovered 2 new moons. Most importantly, humanity finally saw this distant world not as a shining dot in the sky, but as a vast, complex system of a planet, its rings, and, of course, its moons. So it was Pioneer that reintroduced us to this world. Strictly speaking, there probably was never a first discovery of Saturn. One of the most majestic objects in the solar system is visible to the naked eye, and in fact, it's the most distant planet that can be seen this way. So it seems Saturn has always been known, and cultures across the globe have given it various names and tied it to their mythologies. The Babylonians even managed to record its slow movement across the sky. The name we use today, Saturn, comes from the Roman god of wealth and agriculture. And like many Roman deities, this myth was borrowed from Greek mythology, where his counterpart is the Titan Cronus. So Cronus, or Saturn, is visible in the sky without any equipment, and it shines brightest when its rings are tilted most directly toward Earth. In 1610, Galileo Galilei observed those rings for the first time using his primitive telescope. However, he interpreted what he saw as 3 stars touching one another, with the central one appearing 3 times larger than the ones on either side. 2 years later, Galileo saw only a single star and was puzzled. Where had the others gone? Eventually, the strange appendages returned, only to disappear again sometime later, once more leaving Galileo confused. It wasn't until 45 years later that Christian Huygens finally understood what was going on. Together with his father, he built a more advanced telescope and was able to identify the true nature of Saturn, and he also discovered Titan. Huygens realized that the ring plane was sharply tilted relative to Saturn's orbit. This meant the appearance of the planet had to change as both Earth and Saturn moved around the Sun. Galileo hadn't seen the rings because Earth had crossed the ring plane, making them nearly invisible for a time. And take a moment to appreciate just how detailed the diagram Huygens drew actually was. This was the year 1659, still the early days of telescopic astronomy. Yet that didn't stop him from figuring out the structure of a planet that lies over 1.5 billion kilometers from Earth. Yes, Saturn's orbit lies 9.5 times farther from the Sun than Earth's. As a result, it takes about 29.5 Earth years for Saturn to complete a single orbit around our star. And since Galileo first looked at it through a telescope, 14 Saturnian years have passed. Like Jupiter and most other planets in the system, Saturn's orbit is almost a perfect circle. However, its axis is significantly tilted by 26.7 degrees relative to its orbital plane. That means Saturn experiences well-defined seasons, each lasting over 7 Earth years. Winters there are especially frigid, not just because of the reduced sunlight, but also because the winter hemisphere gets shaded by Saturn's giant rings. This creates a striking contrast between seasons, on a planet with no solid surface and no one around to feel it. Another result of this pronounced tilt is that Saturn's rings appear at different angles to Earth observers, ranging from 0 to nearly 30 degrees. This gives us about 15 years to observe one side of the rings, say the northern side, and then another 15 years to see the southern. Indeed, there's a brief window of time when the rings are nearly edge-on and almost invisible, which is exactly what Galileo experienced. The last time the rings disappeared was in March of this very year, 2025, and at the moment of this video, they're just starting to reappear from the southern side. They'll reveal their full splendor again in 2032, when Saturn's tilt reaches its maximum. For a long time, it was incredibly difficult to determine how fast Saturn rotates around its own axis. After all, how do you measure rotation when there are no fixed reference points, no solid surface you can track? Clouds aren't ideal. They move at different speeds depending on latitude. For example, near the equator, they complete a full rotation in about 10 hours and 10 minutes, while at 40 degrees latitude and beyond, the period increases by about half an hour. So in such cases, scientists rely on the planet's magnetic field. Its rotation should, in theory, directly reflect the rotation of the planet itself. However, Saturn's magnetic field is extremely symmetrical. Its variations are so small that they're nearly impossible to detect and measure precisely. Voyager 1 did detect some variation in the form of short bursts of radio waves. Based on that data, Saturn's rotational period was estimated to be 10 hours and 39.4 minutes. But the most accurate measurements came later, from the Cassini spacecraft, which in its final orbits passed inside Saturn's ring system. Here's the thing, the rings act like a natural gravity radar. They respond to tiny changes in the planet's gravitational field. If there are irregularities in the way Saturn's mass is distributed deep inside, then as the planet rotates, it sends subtle impulses to the particles in the rings. Put simply, Saturn's gravity creates tiny ripples in the rings, and Cassini detected them. Because those ripples are tied to the planet's internal rotation, scientists were finally able to calculate Saturn's day in 2019, 10 hours, 33 minutes, and 38 seconds. And now, the speed of Saturn's winds is measured as the difference between the planet's actual rotation and the movement of its clouds. Of course, a planet with no solid surface also has no sharply defined boundary. So, astronomers agreed that for gas giants, the surface ends where the atmospheric pressure equals 1 bar. That is, the same pressure as sea level on Earth. Based on this, Saturn's equatorial diameter is 120,536 kilometers, about 9.45 times that of Earth. Meanwhile, its polar diameter is 12,000 kilometers smaller, making Saturn the most flattened planet in the solar system. Even a modest backyard telescope can reveal this squashed shape, which is caused by the planet's rapid rotation. In fact, this flattening and high spin rate create a curious effect. Any object at Saturn's equator would feel only 75% of the gravity experienced at the poles. So, the gravitational acceleration there is just 8.96 meters per second squared, which is less than on Earth. meaning if you somehow managed to stand on something solid there, you'd actually feel a bit lighter, despite the fact that this is a massive gas giant. And of course, we can't skip over Saturn's average density. Although the planet is 95 times more massive than Earth, it occupies 766 times the volume. As a result, its average density is incredibly low, just 0.69 grams per cubic centimeter. That's only 12% of Earth's density. In fact, Saturn is the least dense planet in the entire solar system. Because its density is lower than that of liquid water, popular science often likes to portray Saturn floating in a giant bathtub. And hey, I'm a popular science channel too, so who am I to break with tradition? So here you go, enjoy! As you've probably guessed, Saturn's extremely low average density is a direct result of the fact that it's made mostly of molecular hydrogen, with a bit of helium mixed in. But don't assume most of that hydrogen is in a gas state. In fact, Saturn, like Jupiter by the way, is not so much a gas giant as it is a liquid giant, or a fluid giant if you prefer. That's because hydrogen under pressures of 1 kilobar or more no longer behaves like a gas, it behaves like a liquid. And here's the kicker. 99.9% of Saturn's mass exists under pressures higher than that, which means that just 1,000 kilometers beneath the cloud tops, Saturn stops being a gas planet. It becomes a liquid one. And no, there's no sharp boundary deep inside where gas suddenly meets liquid. The transition happens gradually. With depth, hydrogen gets hotter and denser, smoothly shifting from a gas to a fluid. Eventually, under pressures around 2 megabars and temperatures near 6,000 Kelvin, molecular hydrogen undergoes yet another phase change. It turns into something that behaves more like a liquid metal. These conditions likely begin somewhere halfway between Saturn's outer atmosphere and its center. So it's possible that's the region where Saturn becomes metallic. And there's likely a core, one containing elements heavier than hydrogen and helium. That core is estimated to have a mass between 15 and 18 Earth masses. But what it's made of exactly, that's still an open question. The deep interior is fascinating, sure, but let's step back outside because honestly, most of the really exciting stuff is happening up here. Almost every stunning image you've ever seen of Saturn, its rings, or its moons comes from one groundbreaking robotic mission. Of course, we're talking about Cassini-Huygens. This joint mission between NASA and the European Space Agency was the first to enter orbit around Saturn. For 13 Earth years, almost half a Saturnian year, Cassini circled the planet, revealing a breathtaking world of rings, storms, and moons. It watched as all of these components interacted and changed with the seasons. Right now, you're looking at the largest portrait of Saturn ever taken. This is actually a mosaic of 126 individual images captured by Cassini over 2 hours on October 6, 2004. To create this, the spacecraft had to photograph each segment 3 times, using red, green, and blue filters. So what you're seeing are Saturn's natural colors, just as our eyes would perceive them. These images show us that Saturn's atmosphere appears softer and less active than Jupiter's. But that's not always the case. Every 20 to 30 years, a massive storm erupts near the equator, a bright, pale feature often compared to Jupiter's famous Great Red Spot. One such storm was captured by the Hubble Space Telescope in 1990, and this is how it looked in 1994. Unlike Jupiter's red spot, which has lasted for centuries, Saturn's Great White Spot is a recurring phenomenon, appearing and then fading away in sync with the planet's seasons. In 2010, Cassini captured the second-largest storm seen since the early 90s. It started as a single bright head that quickly stretched into a long tail, like milk swirling into coffee. Eventually, that single white patch expanded into a planet-wide storm, something quite different from Jupiter's relatively steady red vortex. Spectroscopic data from Cassini revealed that the storm consisted mostly of ammonia ice crystals mixed with a significant amount of water ice, giving it that bright white appearance. But the true trigger behind these giant storms? Still a mystery. One hypothesis, proposed by Caltech researchers, suggests that the culprit is water, specifically how it behaves in Saturn's atmosphere. Heavy, moisture-laden air tends to sink deeper, leaving hydrogen and helium up top. That's the usual state, when Saturn appears calm. But as hydrogen and helium slowly radiate their heat into space, they become denser and begin to sink too. This creates an opening for warm, moist air to rise again, kicking off a massive storm. And why do these storms happen every 20 to 30 years? Well, that's how long it takes hydrogen and helium to cool enough to trigger this cycle again. This doesn't seem to happen on Jupiter. The reason? Saturn's interior is thought to be much wetter. Jupiter's atmosphere contains less water vapor, so these kinds of storms are far less likely to form. In total, 6 great white spots have been documented so far, with the most recent in 2010. All of them occurred near the equator or in the northern hemisphere, but astronomers are still waiting to see one erupt in the southern hemisphere. Now that Saturn's rings are no longer blocking our view, more of the south is coming into the light. So the next giant storm, it might just appear where we've never seen one before. If you're looking for Saturn's most jaw-dropping atmospheric phenomenon, head north to the planet's north pole. Here lies the legendary hexagon, a massive cloud structure that's famous for its bizarre geometry. Each side of this 6-sided jet stream stretches around 14,500 kilometers, longer than Earth's diameter. We're not exactly sure how long this geometric shape has remained stable, but it's been around at least since the Voyager 1 flyby in 1980. Back then, only a portion of it was visible, so scientists were eager to get a better look with the Cassini mission. But when Cassini arrived at Saturn, the planet's northern hemisphere was deep in winter. The hexagon was shrouded in darkness. For the first few years, Cassini could only observe it in infrared, mapping the heat radiating from the planet. It took 5 Earth years before sunlight finally returned and revealed the hexagon in natural color. Winds inside this polar vortex whip around at over 500 kilometers per hour, twice as fast as Earth's strongest hurricanes, and on a scale 50 times larger. The shape looks so perfect, so cleanly geometric, that it almost seems artificial. But it's not. Scientists believe this pattern emerges naturally when adjacent bands of atmosphere move at dramatically different speeds. This kind of wind shear leads to instability, forming swirling vortices and standing waves. And Saturn's north pole happens to be the place with the sharpest velocity gradient in the entire atmosphere. In fact, scientists have recreated similar polygon shapes right here on Earth using simple tanks of water. By rotating fluids at different speeds, they were able to generate hexagons, squares, octagons, virtually any shape, depending on the speed differences and the fluid properties. So yes, this is a completely natural phenomenon. It's just that Earth doesn't have the ideal conditions to form anything like it. We're 10 times closer to the Sun, receiving 100 times more solar energy. Our days and nights are more extreme, and our surface is incredibly varied. Oceans, land, mountains, snow, all of that creates turbulence. Earth's tiny atmosphere gets disrupted constantly. But Saturn? It's a vast gas giant with a deep, uninterrupted atmosphere, ideal for letting large-scale patterns like this form and persist. Still, that doesn't mean we fully understand it. One of the biggest open questions is, why is this vortex so stable? Storms on Earth last days? This one? It's been going for decades, possibly even centuries. No one knows for sure. In 2012, Cassini flew directly over Saturn's poles, capturing the hexagon in motion. Aside from the giant central vortex, you can see smaller reddish ovals swirling around it. For scale, that bright oval in the lower right corner, it's about 3,500 kilometers wide, twice the size of any Earth storm. And about those colors, don't take them too literally. What you're seeing here are false colors used to highlight atmospheric chemistry. In true color, the hexagon looks more like this. Interestingly, scientists noticed that over the course of 4 years, the region gradually turned more yellow. They believe this is seasonal, caused by increased sunlight during Saturn's summer, which triggers photochemical reactions in the atmosphere. These reactions break down methane and form more complex organic aerosols, essentially atmospheric smog. And yet, there's another mystery. The southern pole doesn't have a hexagon. Cassini did observe a giant cyclone there, symmetrical and striking like an enormous eye, but no geometric structure. Why one pole has a hexagon and the other doesn't remains an open question. Whatever the answer is, it seems that each pole on Saturn hosts its own unique weather system, one more cosmic puzzle waiting to be solved. The most beautiful planet in the solar system? Well, after Earth, of course? Sure, it's subjective, but I think everyone would agree that Saturn's rings are an astonishing sight. As you may know, the other gas giants also have ring systems, but none compare to Saturn's in scale or beauty. The fact that Saturn's rings aren't a single solid structure became known to science as far back as the 18th century. It was the mathematician Pierre-Simon Laplace who first proposed that the rings must consist of many smaller rings, as a continuous solid ring simply couldn't be stable. Then, in 1857, James Clerk Maxwell expanded on this idea by mathematically proving that the rings couldn't be solid at all. They had to be made up of countless small particles orbiting the planet independently. But how could this be confirmed? Surprisingly, it happened well before the space age, in the late 19th century, thanks to American astronomer James Edward Keeler. By studying the spectrum of light reflected from the rings, he noticed a distinctive blurring of spectral lines. This indicated that different parts of the ring system were moving at different speeds, evidence that the rings were composed of individual particles orbiting at varying distances. This was the first direct confirmation of Maxwell's theory, and a key piece of evidence showing the rings are indeed made of countless small objects. So, what are Saturn's rings actually made of? Why do they exist around giant planets but not small ones? These are questions scientists began to explore. The first to offer a solid explanation was French astronomer Édouard Roche in 1849. He realized that tidal forces, like the ones the moon exerts on Earth's oceans, might be the answer. Our moon pulls on one side of the Earth more than the other, creating tides. In a similar way, Roche considered what would happen if the moon got too close to Earth. The tidal forces it felt from the planet would grow stronger and stronger until they could actually rip it apart. Roche demonstrated that there is a critical distance within which a moon would be torn to pieces by tidal forces. This is now known as the Roche limit. All the debris from such a catastrophic event would remain in orbit and potentially form a ring. Roche showed that if a moon has the same density as the planet it orbits, the minimum stable distance is about 2.44 times the planet's radius. Anything closer risks being destroyed. For Saturn, this Roche limit lies at around 87,000 kilometers from the planet's center, just about where its thin F ring is located. For Earth, the Roche limit is only around 10,000 kilometers, about 40 times closer than the moon's current orbit. So if a massive asteroid or comet were to enter Earth's orbit within that distance, we too could end up with rings. It's important to note, though, that this restriction applies only to large moons held together by gravity. Smaller bodies, where molecular bonds are stronger than gravity, can survive intact even within the Roche limit. That's why small moons, just a few kilometers across, can persist within this boundary for long periods without being torn apart. What exactly approached Saturn and when it was torn apart is still a matter of debate. The overall shape and mass of the rings suggest it was unlikely to be something particularly large or massive. Despite stretching out some 282,000 kilometers from the planet, the rings are also incredibly thin, on average, just about 100 meters thick. So for all their majestic appearance, their total mass doesn't exceed 40% of Saturn's small moon Mimas. And for context, Mimas doesn't even make the top 5 largest moons of Saturn. Or to give you an even clearer comparison, the mass of the rings is roughly 2/3 that of all the ice covering Antarctica. For decades, the dominant idea was that Saturn likely destroyed one of its former moons, or perhaps a massive comet. But the problem with this explanation lies in the chemical composition of the rings. They're made of 99.9% water ice. Even comets, icy as they are, still contain a much higher proportion of dust and rock. One of the more recent studies suggests that not one, but 2 moons might have been involved. Simulations showed that a collision between 2 icy moons would naturally produce mostly icy rings. During such an impact, the rocky cores of both bodies don't spread as widely as the outer icy layers. After running nearly 200 different simulations, scientists concluded that such a collision could eject enough ice inside Saturn's Roche limit for it to settle into rings. If that's really what happened, then the event was geologically recent, within the last few 100 million years. Why do scientists think the rings are so young? One of the best indicators of their age is the amount of micrometeorite dust that has settled on them. The more dust, the older the rings. But Saturn's rings are incredibly bright, and during its mission, Cassini literally skimmed the edges of the rings and collected particles for analysis. The amount of dust it measured confirmed the youthful nature of the rings, perhaps no older than 100 million years, which means they might have formed while dinosaurs were still roaming the Earth. But then again, it's also possible that constant collisions between ring particles keep exposing fresh, clean ice, so the debate about their true age is still very much ongoing. Of course, Saturn's rings have their own classification, which can be summed up in a few words as a few large rings divided into an uncountable number of smaller ones. Their structure can be studied at many different scales, but it's best to start with the three main rings labeled C, B, and A. These letters were assigned in the order of their discovery, so, oddly enough, ring A isn't the closest to the planet. As we've already mentioned, the main rings span a total width of 282,000 kilometers from Saturn, meaning all three of them would easily fit in the space between Earth and the Moon. Rings A and B are separated by a massive gap almost 5,000 kilometers wide, 4,800 to be precise, known as the Cassini division, named after Giovanni Cassini, who first observed it in the 17th century. Although this area appears empty when viewed from Earth, that's not really the case. The Voyager spacecraft revealed that it actually contains plenty of ring material, just at a much lower density. The same, by the way, applies to many other so-called gaps in the rings. Ring B extends from about 1.52 to nearly 1.95 Saturn radii and is the brightest, widest, and most massive of the three main rings. While the average thickness of the ring is between 5 and 15 meters, this is where the tallest vertical structures have been found, reaching up to 2.5 kilometers high. These pseudo-mountains tower above the ring plane and cast long shadows across the icy surface. Their exact origin remains uncertain, but the most likely explanation involves the gravitational influence of small, yet-to-be-identified moons that seem to splash ring material into vertical arcs. We'll explore the role of moons in ring structure more deeply in the second part. The ring closest to the planet, ring C, is significantly dimmer than the other two, which is why it wasn't discovered until 1850. It's more transparent than rings A and B, reflecting only about 5 to 12% of the light that hits it. And yet, it's not even the most transparent ring. Inside ring C lies an even more elusive structure, ring D, now considered the innermost of all Saturn's rings. The difference in brightness between these two inner rings is quite striking. Ring D has such low density that it barely affects starlight or radio waves passing through it. Its outer edge starts where ring C ends, and its inner boundary fades away just 2,000 to 3,000 kilometers above Saturn's clouds. So in reality, the gap between the rings and the planet itself is much thinner than it might seem. And it was through this very gap that Cassini dove during the final phase of its mission. In those stunning images, you can see the rings as they appear from Saturn's own perspective. Finally, the outermost of the main three is ring A, stretching from about 2.02 to 2.27 Saturn radii. It begins just beyond the Cassini division, but as astronomical technology has improved, it's become clear that this is far from the last ring. Ring F, for example, was first observed by the Pioneer 11 spacecraft. It lies just 3,000 kilometers beyond the outer edge of Ring A, separated by what's known as the Roche division. Ring F is a curious one. It's extremely narrow, just a few hundred kilometers wide, but structurally very complex, resembling a tightly wound spiral. Since this ring is heavily influenced by nearby moons, we'll explore it in greater detail in the next section. Even farther out from Saturn lies the extremely tenuous G ring, first spotted in Voyager data back in November 1980. Despite being around 8,000 kilometers wide, It's so faint that it was originally detected only through its influence on charged particles in Saturn's magnetosphere. To even show it in Voyager images required heavy post-processing to separate the ring from background noise. The origin of the G-ring was a mystery for a long time, but since 2008 it's been linked to a small half-kilometer-wide moonlet, and possibly several others, that eject fine particles into space, effectively feeding the ring with material. Interestingly, when Cassini first entered Saturn's orbit, its trajectory was carefully aimed to pass right through the gap between rings F and G. And while the particles there are incredibly tiny, the spacecraft, speeding through at immense velocity, still felt their impact, particularly on its antenna. The mission team even converted these countless collisions into audio, which you can actually listen to today. Finally, there's Ring E, also directly connected to one of Saturn's moons, likely its second most famous after Titan, Enceladus. This ring is exceptionally wide and diffuse, and Cassini's observations confirmed that it's being actively replenished by Enceladus's geysers, the same ones erupting from its south pole. This ring is enormous, spanning from 3 all the way to 8 Saturn radii, making it one of the largest in the system. And yet, incredibly, it's still not the biggest, because Saturn has one more truly astonishing ring, this one associated with its distant, irregular moon Phoebe. Countless micrometeoroid impacts on Phoebe have dispersed a vast cloud of particles across an immense region of space. In fact, it's hard to even call this structure a ring in the traditional sense. It's unlike any of the others. For one, it's enormously thick, about 40 Saturn radii from top to bottom, and at the same time incredibly wide, stretching from 50 to 270 Saturn radii outward. The particle density is so low that the disk can't be seen through optical telescopes. Instead, it was first identified in 2009 using infrared data from the Spitzer Space Telescope. As of now, it holds the title of not just Saturn's largest ring, but the largest planetary ring in the entire solar system. When the Cassini probe carried out its final orbits above Saturn's thick cloud tops, it managed to send back a wealth of crucial information about the planet. Among other things, scientists were able to confirm a long-standing suspicion. Saturn's ring system is dynamic. It had a beginning, though we still don't know exactly when or how, and it will definitely have an end. Cassini's data made it clear that the particles in the rings are constantly jostling, colliding, breaking apart, and gradually falling onto Saturn. In some regions, these collisions are so frequent that icy chunks are ground down to grains as small as dust. And such grains don't last long. Their tiny size means Saturn's gravity and orbital dynamics can no longer hold them in place. On top of that, these tiny particles are especially vulnerable to high-energy ultraviolet photons from the sun. When exposed, they lose electrons. They become ionized. That is, they're no longer electrically neutral. Now charged, these particles begin to respond to Saturn's magnetic field, which, as you might expect, passes straight through the rings and arcs toward the planet's poles. So the particles start spiraling along magnetic field lines and eventually rain down onto Saturn itself. This phenomenon, where ring material rains down onto the planet, has been dubbed ring rain. And during its daring dives between the rings and the planet, Cassini directly detected this very flow of material, composed mostly of water ice along with some other compounds. The scale of this rain is staggering, somewhere between 5 and 45 tons per second. That's an enormous amount, even by Saturn's standards. And this rich, constant downpour confirms what many had suspected. The rings of Saturn are not eternal. They probably didn't form alongside the planet, and at this rate, they'll be gone within the next 300 million years. Tiny micrometeoroids relentlessly pelt the rings, gradually knocking material loose. Meanwhile, Saturn's moons, some orbiting within the rings themselves, scatter and disturb the ring matter as well. All of this adds up to a clear conclusion. The ring system is ephemeral. It won't last long on the timescale of the cosmos. It's a fleeting crown for Saturn, and it just so happens that we're alive to witness it. Hard to imagine that human civilization could survive another 300 million years, but if, by some miracle, it does, our distant descendants may live to see Saturn lose its rings for good. And next time, it won't just be an optical illusion. But for now, while they're still here, they continue to amaze us, both in their grandeur and in their ongoing interactions with Saturn's many moons. To be honest, splitting the discussion of rings and moons into separate parts might not have been entirely fair, because together they form one big living system. In fact, the whole Saturn system is like a miniature solar system of its own, and it deserves a story with no limits on runtime or curiosity. So we'll dive into that in the next episode, exactly 1 week from now. Stay tuned. And in the meantime, check that you've hit the like button and maybe dropped a comment below. Thank you all so much. See you in the next episode, and take care of yourselves.